One, two, one, two. day, grade 12 learners and teachers. Welcome to today's mathematics lesson. My name is Sibusiso Shongwe. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saipono Discovery Center. Right, this lesson stems from the previous lesson that we've had on the counting principle, which I named part 1. This is part 2 of the fundamental counting principle. Those of you who did not get time to look at part 1 of this, you can always log on to www.pocketschool.co.za to check our part 1, which was in August. This is a continuation from that particular lesson. Remember, we are available on WhatsApp to answer all your questions. Our WhatsApp interactive number is 064 748 8913 064 748 8913. As the lesson progresses, it will be appearing at the bottom of the screen. Right, we look at the fundamental counting principle. Now, our lesson objectives for today would be we should be able to use the fundamental counting principle to solve problems involving digit numbers and codes. We should be able to use the counting principle to arrange identical objects. We should be able to use the counting principle to count the rest of the items in problems where counting what is described becomes difficult or tedious. And we should be able to apply counting principle to solve probability problems. Remember, the overall theme is probability. At the end, we should be able to apply our knowledge of the fundamental counting principle to solve probability related problems. Right, you can refer to page 49 of the CAPS document or the exam guideline that was published in 2021 on page 7 to check what would be required of you as you do the counting principle. Right, to start off, we're going to start off with our digit codes. We came up with some useful guidelines that you can use when you deal with digit codes. Suppose that the question is asking you about divisibility. It's only, they say, maybe the code is divisible by a certain number. Then you need to check the first and last digit. Usually you check your last digit, whether the last digit is divisible by that number. If it is, then that code is going to be true. Right, greater and divisible. The last digit must be divisible by that number. Note that 0 is divisible by any number. Greater than or equal to, from that number and above, that particular number is included because they say greater than or equal to. Greater than, when they say the code is greater than, the number is not included. Usually what we do is from the overall codes that we've determined, we're going to subtract 1 from the final answer because we want to make sure that that particular number which was included should be excluded. The code that was included by our counting procedures should then be excluded. Greater and even, the number involved must be the first digit in the position given. Even number must be the last digit in the position given. If they say greater than a specific number and also even, it means you are looking at the two conditions. You are looking at the leading variable, the leading number. You are also looking at the last digit there. Subtract 1 from the final answer if the digit must be greater than, because remember, if they say greater than, they do not include that particular number, so you have to subtract 1. Between two numbers, maybe they say the code lies between 5,000 and 6,000, then it means that the code will then lie between the two numbers, which means the first digit must start with that number that they gave you, and the last digit as well must also end with a particular number that was given there, and then we need to arrange the remaining digits. So those are the guidelines that we can use when we deal with digit codes. Right, let us look at an example codes and see how we can apply our guidelines to try and solve some code problems. The first one is the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 are used to make a 3-digit number. Very, very important. This number contains only 3 digits. However, you have the numbers available to you, which means that your sample space, the number of elements that are in your sample space, we have numbers from 0 to 9, which means that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers that are available to use. Right. However, we are forming a 3-digit code or a 3-digit number. How many unique numbers are possible if no digit may be repeated and the number may not start with a 0? No digit may be repeated and the number may not start with a 0. That is the first one. We are looking for the total codes here. They are saying it should be a 3-digit code. So we have 1, 2, 3. We open 3 spaces for those 3 digits. They are saying no digit may be repeated, which means we are not allowed to repeat a digit, and the number may not start with a 0, which means that the leading number, the first number in that particular code must not be a 0. Now we want to determine the total number of unique numbers that we can form here. Now, what we're going to do is we're going to ask ourselves for the first position, how many numbers do we have at our disposal for the first position? Obviously, our sample size has 10 numbers, which means that now we should be having 10 numbers. However, there is a condition there that it may not start with a 0, which means that we have 9 numbers to use. We have 9 options for the first digit, which we can then put 9 there. And then for the second digit now, since we've used 1 digit, we should be left with 9 again. Let me explain how. Remember, when we started, we had 10 numbers. And out of the 10 numbers, they said we should not use 0. So we have 9 options of filling the first position. When it comes to the second position, now that we can use the 0, it means that now we still have 9 numbers because we've used 1 in the first position. So we are left with 9 numbers to use here. And then in the last position, since we've used 2 numbers out of 10, we'll now be left with 8 options to fill the last position. Now, if you calculate all that, you get that the total numbers that can be formed using your calculator, it would be 9 times 9 times 8, which gives us 648 numbers. So there are 648 unique numbers that you can use in this case. Right, moving right along. The second one, they say the number must start with an even number and then alternate between odd and even numbers. Repetitions are allowed and the number 1 may not be used. You see, you have some conditions here. The condition is that you should have this numbers alternating between even and odd. That is the first condition. Another one is that you are allowed to repeat a number that you've used before. That is the second condition. But we have another condition here that the number 1 may not be used, which means 1 is removed from the sample size, which means that now in our universal set or in our sample space, we now have 9 available numbers. Now we want to have a 3-digit code. So 1, 2, 3, we open 3 spaces to fill in those options that we might have of having those codes. Now, remember, they said it must alternate between odd and even. It must alternate between odd and even numbers. So we have that, we have even, odd, even. It alternates between odd and even numbers. Now, if you have that particular condition where you want to alternate between odd and even numbers, we can check here. Out of our sample size, how many even numbers do we have? Even numbers, we have 2, 4, 6, 8, including 0. So the number of even numbers should be given by 5. Let's check the odd numbers. the odd numbers in this sample size would be 1, but 1 is excluded from the sample size, so we exclude 1. It will be 3, 5, 7, and 9. So we have that the number of odd digits in this case should be 4. So if it alternates between odds and evens, if it alternates between odd and even, let me start with odd because they said it alternates between odd and even. So if I start with odd, then even, then odd. Then how many odd digits do I have? I have 4 odd digits. So I have 4 options of filling the first position. Now when it comes to the even digits, I have 5 of them. So it means that I'll have 5 options of filling the second position. Now when it comes to the last position, I want to use odd digits again. Remember, I had 4 odd digits. I've used 1 in the leading position. However, since repetitions are allowed, I can still use that particular number which I used in the leading position. So I still have those 4 digits. Now to calculate the total number that should be formed here, I'll have 4 times 5 times 4. This gives me 80 numbers. So I can have 80 unique numbers. Right, moving right along to the last one now. The last one, they say the last digit must be a 0 and repetitions are not allowed. Now, if you look at this question, you can see that there are 2 conditions. The first condition is that the last digit must be a 0. So you should have 0 in the last position. The next one is that they say repetitions of digits is not allowed. So you cannot use 1 digit more than 1 time, right? Which means that now if we open our 3 spaces, remember these 3 spaces are representing the number of digit or rather the digit number that we are interested in. It should have 3 numbers. So now if we check in the first position, then let's start with the condition. The condition says the last digit must be a 0. So you must have a 0 here. You must have a 0 there. That's where we're going to start. So we're going to ask ourselves now, how many options do we have of having zeros in the last position? Since there is 1 0 in the sample size, it means that there is only 1 option of having a 0 in the last position. Now we can fill in the rest of the positions there. Now the first position, they say since repetitions is not allowed, how many numbers do we have? The sample space has 10 numbers. We've already used 0 in the last position, which means that we have 9 options of filling the first position. The second position, since we've used now 2 digits, we've used 0 in the last position and we've used another number in the first position, which means that we've used 2 out of 10. We are now left with 8 numbers. Now, if you multiply to get the total number of numbers that you need, it's 9 multiplied by 8 multiplied by 1. So this is 72 numbers. So that's basically how you should be working with these particular digit numbers. In this case, you look at the conditions and then from there, you are going to make sure that you abide by the conditions that they gave you in order for you to get the correct answers. Right, I move on. Now you can see it's an activity. It's an activity. Immediately, you guys should try working on this now. I am going to give you, since there are 4 questions, I'm just going to give you about 5 minutes for you to be able to solve those questions. Please make sure you solve them to the best of your ability. You have 5 minutes to do so, and your time starts now. Hello and welcome back. I hope you enjoyed playing around with these digit codes. Right, let's look at the problem together. The digits 1, 2, 3, 4, 5, 6, and 7 are used to make a 4-digit code. How many unique codes are possible if digits can be repeated? Digits cannot be repeated. The code is even without repetition, and the code is even with repetition. Now, if you check here, this problem tries to test your ability to solve problems when they say with repetition or without repetition. Right. Now the first one. We are looking for the total codes. Obviously, it's a 4-digit code. So we're going to open those 4 spaces. Now, we open those 4 spaces. They are saying to us, we are making a 4-digit code. And we know that since the numbers 1 to 7, the number of elements in our universal set should be 7. Because we are using 1, 2, 3, 4, 5, 6, and 7. So we have 7 numbers or 7 numbers to use in this case. Now, how many codes are possible if digits can be repeated? If you can repeat digits and you want to form these codes, how many options do you have of filling the first position? Obviously, it would be 7 since we have 7 numbers. So we would have 7 options of filling the first position. Now, if you move on to the second position, since you've used one number there, so when you move to the next position, you still have 7 numbers to use because they said you can repeat the number that you've used. So we also have 7 options of filling the second position. So is filling the third position as well. It should be 7 options because we can use again the numbers that we've used. So we can recycle these numbers and use them once more. So also here would have that this is 7 options. So if you then work it out in the calculator, you get that it's 2401 codes. So you would have 2401 codes if digits cannot be repeated, or if digits can be repeated, right? Now, moving to the second one, what if digits cannot be repeated? How many codes, total codes that we can have in this case? We open 4 spaces because the code that we want to form has 4 digits, right? In the first position, we ask ourselves, how many options do we have of filling that position? Obviously, because we have 7 numbers at our disposal here, then would be having 7 options because any of those 7 numbers has equal chances of filling the first position. Now, if you move to the second position, since you've used 1 digit in the first position and digits cannot be repeated, then it means that now you have 6 options because you've already used 1 option in the first position. Although you had 7 options in the first position, but remember, you only used 1 of them because only 1 number can fit into that particular position. Now, when you move into the third position, you've used 2 numbers already, which means that you'll be left with 5 numbers to use. And then in the last position, since you've used 3 numbers already, it means that you'll have 4 numbers to use. Now, if you multiply 7, 6, 5, and 4, you get that you can have 840 codes. You can see here the number of codes decrease when you cannot repeat a number. So the number of possible codes that you can form are now decreasing. Now the code is even without repetition. See, now they want you to form an even code. We should remember the guidelines that I gave you when we started with our lessons. They said the code is even. So if the code is even, you can now check. Once they say to you the code is even, it means you look at the last position. The last position should contain an even number. If the last position contains an even number, then the whole code would be even. Right, so what we're going to do now, we're going to say, so the total number of codes in this case would be, we are going to open these 4 spaces because we need 4 numbers or a 4-digit code. Now, since they are saying the code is even, then we're going to focus on that condition. That condition would work for the last position. So in the last position, we need to have even numbers. So we define a new subset for the last position. So what would be our even numbers that are in the sample space? It should be 2, 4, as well as 6. These are the even numbers that are in the sample space, which means that in the last position, remember I said the code would always be even if the last position contains an even number, which means that in the last position we define a new subset now which represents even numbers. So now what are the even numbers that are available in our universal set or in our sample space? The number of even numbers that are in the sample space would be 2, 4, as well as 6, which means that in the last position there are 3 options of filling that particular position. There are 3 options of filling the last position. Why am I filling the last position first? Because the condition works for the last position. So that is why I'm filling the last position first. Right, now moving on to the rest of the positions now. Since I've used one number in the last position, I'm now going to have, since it's without repetition, I'm not allowed to repeat. So since I've used 1 out of 7 numbers, means that I'll have 6 options of filling the first position. And then I would then have 5 options of filling the second position, because I've used 1 number in the last position, I've used 1 number in the first position, which means that I have 2 less numbers in the sample size. That is why I'm putting 5 there. Now to fill in the third and last position in this case, I'm going to have 4 options because I've already used 3 options. So if I put that on my calculator, I get that the number of codes becomes 360. So if I want even codes, then those codes would be given by 360. Right, let's work with the last one. The code is even with repetition. So it's the same approach. 1, 2, 3, 4. We are defining a new sample size or a subset for the last position, which should be a subset that is limited to only even numbers. So I will have 3 options of filling the last position. Now I go to the first position. Since I have 7 numbers at my disposal, I've used 1 in the last position, but I'm allowed to repeat because they said with repetition. So I can have 7 numbers to use there. I can use 7, or I have 7 different options to use in the first position. Also in the second position, I would have 7 options. Also in the third position, I would have 7 options because I'm allowed to repeat the numbers that I've used. If I put that on the calculator, I'm going to get that this becomes 1029 codes. So that is how you were supposed to work out this particular question. Right, let's move on. Now we move on to problems that are now a bit complex or that are a bit challenging. Not that much, just a bit. So we are increasing the degree of difficulty or the cognitive demand or the cognitive levels in this case of these code problems. Now let's see how we can work with questions on digit codes that are pitched at higher cognitive levels. Right, the digits 0, 1, 2, 3, 4, 5, 6, and 7 are used to make a 4-digit code. How many unique codes are possible if? Now let's check our sample size. The number of elements in the sample size of the universal set in this case should be 8. Why is it 8? It's because we started at 0 in this case. Now let's check the first one. The code has numbers greater or equals to 4,000 and divisible with 2 or divisible by 2 with repetition. You see, now there are certain conditions that we need to understand and deal with when we solve this particular problem. Right. Now, let's check how best this problem can be solved. They say the code has numbers greater than or equals to 4,000 and divisible by 2. So for the code to be divisible by 2, it means that you should have factors of 2 as the last digit. So in your last digit, you should have factors of 2 or multiples of 2, or you should have numbers that are divisible by 2 on the last position, which means that if we form the code, obviously we are forming a 4-digit code. They said the code must be greater or equals to 4,000, which means that the first digit must start with what? It must start with the number 4 and above, because they said must be greater than or equals to 4,000. So it's from 4,000. If you can look at the range of these codes here must start from 4,000 up until, obviously, the biggest one should start with the number 7. And if you are allowed to repeat, the biggest one will contain all the biggest numbers, but the last number should be the biggest factor of 2, or the biggest number in the sample size that is divisible by 2. So that would be the range of the codes that they want you to obtain in this case. Now, it means that we need to start with the first variable and check the subset that we can define for the first variable. They said the number must be greater than or equals to 4,000, which means you can start with 4, 5, 6, or 7. All those codes that start with 4, 5, 6, and 7 are codes that contain numbers that are greater than 4,000. However, it should also be divisible by 2. Now, we check in our sample size the numbers that are divisible by 2. In this case, the numbers that would be divisible by 2 would be 0, 2, 4, as well as 6. So those are the 4 numbers that would be divisible by 2. So how many options do we have of filling the first position? It's 4. How many options do we have of filling the last position? It is also 4, because the repetitions are allowed in this case. So if you've used 4 here, you can still use 4 there. Or if you've used 6 here, you can still use 6 in the last position. So now the first and last positions have been filled, because that is what the condition demands of us. Now let us check how we can fill in the rest of the numbers. Now, the second position, obviously, we have 8 numbers at our disposal, and each number has equal chance of being used there. So we can use 8, or we have 8 options, and also here we can use 8 different options there. So the total number of codes in this case would be 4 times 8 times 8 times 4, which gives us 1024 codes. So these number of codes that we are interested in this case would be 1024, 1024. Right, let's move on to the second question quickly. The code has numbers greater than 4,000 and divisible by 2 with repetition. Now, if you check the second one, they just said greater than 4,000, which means that 4,000, we have the same range. However, 4,000 must not be included. You see, this one, 4,000 is included because they said greater than or equals to 4,000, which means that 4,000 is included. However, here, 4,000 is excluded by the condition. So the condition excludes 4,000, but the first condition included 4,000 because they said greater or equals to. But now the second one says greater than. So this condition naturally excludes 4,000. Now, however, in the number of codes that we're going to determine, 4,000 would be included in those codes. So we need to then exclude it. That is why in the guidelines, I mentioned that 1 should be subtracted from the final answer. That is because we want to take away 4,000, because 4,000, according to the condition, must not be included. Right, they are saying also with repetition. So we still have 4 digits, 1, 2, 3, 4. Now we have 4 options of filling the first position, because in the first position we want numbers that are greater than 4,000. That would be 4, 5, 6, and 7. Those are the variables that would give us codes greater than 4,000. In the last position, since we are looking for codes that are divisible by 2, that would be 0, 2, 4, as well as 6. So here we'll have 8 and 8, because we are allowed to repeat those codes. So the total number of codes in this case should be 1024. That would be 4 times 8 times 8 times 4. However, we need to subtract 1 from the overall codes, because these codes, this codes that we get, the 1024 codes, include 4,000. However, the condition naturally excludes 4,000, because it says it should be greater than 4,000. So we're going to get this as 1023 codes. So we get 1023 codes. So that is how we work with the second one. Remember, I told you that these questions would be pitched at a higher cognitive level. You should be able to deal with them. Right, let's look at the last one. The last one now, they say the code is in between 4,000 and 5,000. Normally, in most of your books, they'll just write between 4,000 and 5,000. It's the same thing here. It's the same thing, but we wrote it in terms of, or in the form of, a compound inequality. The code must be greater than 4,000 but less than 5,000. So in order for us to get a code that is greater than 4,000 but less than 5,000, we obviously are forming a 4-digit code. For it to be greater than 4,000 but less than 5,000, we need to start with the number 4. Because the range of this code, it should start with 4,001 and should end with 4. The biggest numbers in this case would be 4. That would be less than 5,000 from our sample size. 7, if it's with repetition, 7, 7. That would be 477. That would be the range of these codes, because these codes must start from greater than 4,000 but less than 5,000. Remember, a number that is less than 5,000 starts with a 4. A number less than 5,000 starts with a 4. That is why we are saying only 4 should be the leading number. It's only 4 in the subset for the leading variable. Now, how many options, or rather how many 4s do we have in our sample size? Or how many options do we have of filling the first position? Since there is only 1 4, we have 1 option of filling that first position. Now the second position, since we can repeat numbers, we now have 8 available numbers to use, because repetition is allowed. The third one, we still have 8 because repetition is allowed. The last one, we also have 8 because the repetition is allowed. Therefore, our total codes in this case would be 1 times 8 times 8 times 8, which is 512. However, this 512 that we just got, it includes 4,000. It includes 4,000. However, the condition indicates that the code must be greater than 4,000. That is why I gave you this range here. The first number that should be used, the first code should be 4,001. The answer 512 includes 4,000 in this case, because we said we can use 1 4 and then we can use all the other numbers there, which means we can use 0 0 and 0 there. on the second, third, and fourth position, which means that this code that we just got includes 4,000. So in order to take away that 4,000, we're going to subtract 1. So the total codes in this case would be 511 codes. That's basically how you work with this question, which is pitched at a slightly higher cognitive level. You have to look at the condition and work with your answers based on the given condition. Right. Now, let's move on to the next one. Example 3. I indicated that's a challenge example. This is also pitched a bit higher. It can be a level 3 or a level 4 question, but it is pitched at a higher cognitive level. It's a level 3 difficult question or just a level 4 question in this case. Now, we are given the digits 1, 2, 3, 4, 5, 6, and 7, and they are used to make a 4-digit code. Now, the number of elements that are in this sample size are 7 elements. 0 is not included there. And then they say how many unique codes are possible if the code is even and greater than 4,000 or 3,000 without repetition. The code is even and greater than 3,000. Remember, for the code to be even, the last position must contain even numbers. If the last position contains even numbers, then the overall code in this case would be even. And then if the code is greater than 3,000, then the leading variable should contain numbers starting from 3 and above, because they said it should be greater than 3,000, which means that we can define our subsets for the first variable, for the first digit as well as the last digit. For the first digit, we can have numbers that starts from 3, so this is 3, 4, 5, 6, and 7. All these numbers are going to give us codes that are greater than 3,000. Now, since the code should be even, the last position should contain an even number. In this case, the even numbers that are available at our disposal are 2, 4, as well as 6. 2, 4, as well as 6. Now, if you look at this problem, since they said without repetition, then we start having problems. Because they said without repetition. Why are we having problems? Look at 4 as well as 6. 4 and 6 are in both the leading variable as well as the terminating variable, or the leading digit or the leading number as well as the terminating number of this particular code. So if 4 is used in the first position, if in the first position you make use of 4, then it cannot be used in the last position. Now, the problem that we will have here is that the fundamental counting principle is concerned with the options that we have. So how sure are we that we've used the 4 in the first position or we've used the 4 in the last position? We cannot be sure generally when we use the counting principle because it's concerned with the number of options that you might have. So we have a problem here. What is our problem? The problem is that the digit contains 4 and 6 in the leading variable as well as 4 and 6 in the terminating number. So now we need to come up with a strategy of being able to resolve this particular problem. Right, let me repeat what the problem is first so that you understand what the problem is. If here they said with repetition, it was not going to be an issue because if you've used 4 and 6 in the first position, you can also use 4 and 6 in the last position. Now, in this case, they said without repetition. So if you've used 4 in the first position, it cannot be used in the last position. But how sure are you that you've used the 4? Because in the fundamental counting principle, you put all options there. You say, I'll have 4 or 5 options for the first number, and I'll have for the first digit, and I'll have 3 options for the last digit. So in order for us to be sure of using the 4 and the 6, we're going to make use of what we normally refer to as the case method. In the case method, I'm going to resolve this into different cases that are going to permit me to use these numbers and be sure where these numbers are used. Now, if you check, if I use my case method in the leading variable, which means I'll be fixing each and every particular digit in the leading variable. So if I fix 3, I'll have it as case 1, fix 4 as case 2, fix 5 as case 3, 6 and 7 as case 4 and 5 respectively, which means that I would have 5 cases of resolving this problem. However, when I check the last digit, since I have 3 numbers, it means that I can fix 2, I can fix 4, I can fix 6. If I can fix those numbers, I can have 3 different cases, because I'll start by fixing 2, then fix 4, then fix 6. The case method will then allow me to be sure of the number that I've used in the last position. I would be definitely sure that I've used a 2. I'll be definitely sure that I've used a 4. I'll be definitely sure that I've used a 6. So this is how you should be using the case method. So I will use case method is used for the last position to ensure that there is no repetition of digits 4 and 6, because digits 4 and 6 are available in the last position as well as in the first position. So I will take this as the first case, case 1. Case 1, I'm going to fix 2 in the last position. I'm going to fix 2 in the last position. How you use this case method, it is much easier if you're going to fix these numbers one by one. So I'm going to fix 2 in the last position. If I fix 2 in the last position, the total number of codes for case 1 would be 1, 2, 3, 4. In the last position, I use 2, which means that in the first position, I still have 3, 4, 5, 6, and 7. So I have 4 options of filling the first position, and I have 1 option of filling the last position, since I have only 1, 2. Now, as I continue with this, I check now. I've used 2 digits already. I've used a 2 in the last position, and I've used 1 out of the 4 options in the first position. So out of 7 numbers, I've already used 2, which means that I'm left with 5. So here I'll be having 5 options, and then here I'll be having 4 options. Now, if I multiply the 3, then I'll get that this is 1, 2, oh, sorry, I made a mistake in the leading variable. It should be 5. I have 5 particular options here, because it's 1, 2, 3, 4, 5 numbers. It's not 4, it's 5. So this would be 5 times 5 times 4 times 1. This would give me 100. So if for case 1, I obtain 100. Now, the second case, case 2, I'm going to fix now the number 4 in the last position. Remember, I said you fix these numbers one by one. So I could not take the leading variable because I had 5 numbers, which means I was going to have 5 different cases. So to reduce the number of cases, I'll use the last position. So if I fix 4 in the last position, so the total code for case 2 would be given by 1, 2, 3, 4. Here I'm fixing 4. How many options do I have of having a 4? It's 1 option. Now for the leading variable, since I have 3, 4, 5, 6, and 7, since I've used 4 in the first position, it means that now here I have 3, 5, 6, and 7. Because digits cannot be repeated, so I cannot use a 4 again. So I will have here now 4 options because I've used 4 in the first position. Now that I've used 2 numbers, I'm left with 5 numbers to use. So I'll have 5 options of filling this position. I'll have 4 options of filling this one. So this would be 4 times 5 times 4 times 1. This gives me a total of 80 codes for case 2. Now, to kill this off, I'm going to then have the third case, case 3, where I'll now be fixing the number 6 in the last position. So I fix 6 in the last position. If I fix 6 in the last position, this is what I'm going to have here. I'm going to have total code for case 3 would be 1, 2, 3, 4. Since I'm fixing 6 in the last position, I'll put 6 there as my subset for the last position. And then for the first position, now I'm going to exclude 6 from all the numbers that should be greater than 3,000. So I can use 3, 4, 5, and 7. So I'll have 4 options of filling that position. I'll have 1 option of filling the last position. Now I've used 2 numbers. I'll be left with 5 numbers. So I have 5 options here, and then I'll have 4 options here. So the total codes for case 3 would simplify to 80 codes. Now that I've resolved this into 3 cases and I obtained the total codes for each case, then it means that in order for me to complete this problem, I'll then have therefore the total codes overall would be total code for case 1 plus total codes for case 2 plus total codes for case 3. This will then simplify to 100 plus 80 plus 80. This is 100 plus 160. So this would simplify to 100 plus 80 plus 80 should simplify to 260 codes. Simplifies to 260 codes. So that is how you are going to solve this level 4 question. You resolve it into different cases, and then from there you're going to make use of the case method to work out the answers for the case for case 1, the answer for case 2, answer for case 3, and then you add all the answers to get the total number of codes overall that are even and greater than 3,000 without any repetition. Right, that is how you were supposed to solve that challenge example. Right, let us see whether you understood the use of this case method in solving this particular problem. I will give you a problem of your own to work with, and I'll give you about 3 minutes to try and resolve or solve that particular problem. Let's check that problem now. That is activity 2. It's a challenge question. You have 3 minutes to work with this problem. Please solve it to the best of your ability, and your time starts now. Hello and welcome back. Right, I hope you enjoyed playing around with this level 4 type question. Right, let's check this one out. The digits 1 to 7 are used to create a 4-digit code to enter a locked room. How many different codes are possible if the digits may not be repeated and the code must be an even number bigger than 5,000? This question was in November 2016 paper 1. Right, let's check now. We are interested in a 4-digit number 1, 2, 3, 4, and then they said the number must be even, which means that the last position must contain even numbers. The even numbers that are available at our disposal in this case would be 2, 4, as well as 6. And then they say and bigger than 5,000. So the numbers that are bigger than 5,000 obviously are numbers that start with 5. So it would be 5, 6, as well as 7. So those are numbers that are bigger than 5,000. It should be number 5, 6, and 7 out of all the numbers that we have at our disposal. And since they said that the code should be even, then the last position should contain even numbers. In this case, it's 2, 4, and 6 that are available at our disposal. Now, if you check this problem, since they said digits may not be repeated, since you are not allowed to repeat a digit, and you can see here, you have the number 6 and you have the number 6 there. So you cannot use the number 6 in the first position and use it in the last position. So it should be used only once, and we can never be sure whether it was used because the counting principle concerns itself with the number of options that you have. So we're going to resolve this into cases. So we're going to use case method. We can use it for the leading variable or for the last variable. So we can use it for the first variable or for the last variable because it will be 3 cases either way. So for consistency, let me stick to the last variable. So I'll start with case 1. Case 1, I'm going to fix 2 in the last position. If I do so, then this is what I'm going to have. 1, 2, 3, 4. This is a 2 that I fixed there. And then here, I'll have 5, 6, and 7. So here, I'll have 3 options for the first digit. And then I'll have 1 option for the last digit. Now, the remaining 2 positions, I've used 2 numbers already out of a possible 7, which means that I'll be left with 5 numbers here and 4 numbers there. So this would be 3 times 5 times 4 times 1. This would give me 60 codes. And then now I can go to the second case. Case 2. Case 2, I fix 4 in the last position. I fix 4 in the last position. So I would have 1, 2, 3, 4 digits. If I fix 4 in the last position, then I would have a 4 here that I've fixed. And then the numbers in the leading variable will be 5, 6, and 7. So I have 3 options of having the number greater than 5,000. And then I'll have 1 option of filling the last position since I have 1, 4. Since I've used 2 numbers, I'll now be left with 5 here, then 4 there. So it's 3 times 5 times 4. That would give me 60 codes. Right, then we work with our last case. Case 3, we're going to fix 6 in the last position. If I fix 6 in the last position, then I open 4 spaces because I'm interested in a 4-digit code. So if I open 4 spaces here, I know that I've fixed 6 in the last position, which means that now in the leading position, I cannot use a 6. So I can either use a 5 or a 7. I can no longer use a 6. So I have one option of filling the last position, and I have two options of filling the leading position, because I cannot use a 6 twice, right? And then I've used two numbers. I'll be left with 5 numbers to use, so I would have 5 and 4 here. So this is 2 times 5 times 4 times 1. That would give you a total of 40 codes. Therefore, the total number of codes, total codes overall should be given by 60 plus 60 plus 40, which simplifies to 160 codes. So you'll have a total of 160 codes of resolving this. There are so many methods. If you go to the marking guideline of this paper, November 2016, you'll see different methods being used. But this, I believe, should be the easiest method, because you just fix the numbers one by one. It becomes easier for you to work with those possibilities. Right, that's how you are supposed to solve this higher order question. I move on. Arrangement of identical objects. Arrangement of identical objects. If you still remember from our part 1, we've arranged different objects. There was a time when we worked with arrangement of letters, different letters in that case. So now we are working with identical objects. Right, let's look at this particular example. Consider the word Anna. How many different letter arrangements can we make if we consider the two A's as different? The two A's as different. If the A's are different letters, then it means we have A1 and A2. So I want us to try and rearrange these letters and see how many possible arrangements can we have. We started with A1, and then N, then A2. Then we can still start with A1 and then A2 and N. We just interchange the positions of A2 and N. Or we can start with N and have A1 and A2. Or we start with N and have A2 and A1. Or we can start with A2 and then have N, A1, or A2, have A1 and N. So these are the different possibilities that we can have here. You see that we can arrange this in 1, 2, 3, 4, 5, 6 ways. We can arrange this in 6 ways. We can arrange these letters in 6 different ways. That's how we can do it manually. Right, let's look at the second one. If we consider the two A's as identical letters, so if the two A's are identical, then we have A, N, A. So if they are identical, then you can start with A, then you can or alternatively you can start with N and have A and A. Or alternatively, you can start with the two N's and then the last one is N, because these A's are identical. So you can see that the total arrangement that we can have here are reduced to now 3 ways. We can arrange these letters in 3 different ways because the letters are now identical. There's no difference between the A at the beginning and the A at the last position. So we can have 3 ways of arranging these A's. That's how we can do it manually. However, this would not be practical for a bigger weight. Like if you maybe work with Mississippi, then it's going to be a very tedious task for you to can write down the arrangements by manually writing down all those particular different letter arrangements that you can have there. Right, so that brings us to our rule that we can use to simplify problem solving here. So the above example allows us to formulate the following rule. The number of arrangements of n objects of which p are identical and q identical and r identical is given by n factorial over p factorial times q factorial times r factorial and so on. So we can revisit this particular rule here by using we use rule 4 to revisit example 4. Now, if we consider the two A's as different letters, so the total arrangement, if these are different letters, how many letters do we have in total? It's 3, so this would be 3 factorial. And then we check our 3 factorial. 3 factorial gives us 6 ways. So if you remember in the previous problem, we also got 6. But if we consider the two A's as identical letters, then the total arrangement would then be governed by rule 4. The total number of letters is 3 factorial. However, we have that they are repeated letters. And how many repeated letters do we have? We have A's that are repeated twice. So we're going to divide that by 2 factorial. This 2 factorial is for the A's. So if you divide 3 factorial and 2 factorial, if you still remember, this is 3 times 2 factorial over 2 factorial. So this would be 3 ways. This would be 3 ways. If you still remember from the previous one, we also got 3 ways. But now we are making use of our rules there. Right, let's check another example. Example 5. Consider the letters of the word person and how many letter arrangements can we make if the repeated letters are treated as different letters. Now, if we count these letters, it's 1, 2, 3, 4, 5, 6, 7. It's 7 letters. If they are different, then the total arrangement would then be given by what? 7 factorial. So this would be 7 factorial, which is 50, 40. 50, 40. However, if the repeated letters are treated as identical letters, then we would have that the total arrangement, we check now our sample size. We have B, we have 1B, and then A, we have 1A. Letter S, we have 2 of them. Letter O, we have 2 of them. Then letter N, we have 1. This gives us a total of 7 letters. So we would have that the total arrangement would be 7 factorial. Divide by those that are repeated. We are repeating letter S and letter O. So this would be 2 factorial for letter S times 2 factorial for letter O. This is for S and this is for O. Those are the repeated letters. So if we want to work that out, that would be 7 factorial divided by 2 factorial times 2 factorial. That would give us 1260. That would give us 1260. Right, that's how we're going to solve this particular problem. Right, we move on. It's a continuation. They said the word starts and ends with the same letter. The word starts and ends with the same letter. Let's rewrite this again. B1, A1, S2, O2, N1, which gives us 7. So they say the word starts and ends with the same letter. Now, if they say the word starts and ends with the same letter, we can start and end with letter S or start and end with letter O. Since we have 2 possibilities, the first possibility is starting and ending with S. The second possibility is starting and ending with O. So we can resolve this into cases as well. Case 1, we start and end with S. If we start and end with S, then we're going to have S at the beginning, S at the end, and then in between, how many letters do we have? We will have 5 letters that remain. We'll have 5 letters that remain if we start and end with letter S. So the total arrangement for case 1 would be the 5 factorial because we have 5 remaining letters. If we started and ended with S, then it means that we will have only O's that are repeating. So divide by 2 factorial. This 2 factorial is for the O's. So our answer here would be 5 factorial over 2 factorial. This gives us 60 for case 1. However, we can also start and end with letter O. If we start and end with letter O, then we'd have O in the beginning, O in the end, would have 5 letters that remain to arrange. So how can we arrange them? That is total arrangement for case 2 to be 5 factorial divide by, since we only repeating letter S, it would be 2 factorial. This 2 factorial is for letter S. So we're going to have that this is 60. Therefore, the total arrangement overall would be given by 60 plus 60, which is 120 ways. So there are 120 ways in which we can arrange these letters. Right, let's move on. Activity 3, looking at time here, we are actually running out of time, so I'm not going to have time for you to do this activity, so I'll just move on. Arranging the rest. Now we need to know how to arrange the rest of the items. Let's go through this concept and see what would be expected of us. It is sometimes very difficult or tedious to count what is being described, but much easier to count the opposite of what is being described. In such cases, we'll use the rule. Number of possibilities of meeting a condition would always be equals to the total number of possibilities minus the number of possibilities of not meeting a condition. I'll give you an example. Let's say that we want to use at least 1 4. We have a 4-digit number. 4-digit. 1, 2, 3, 4. And the condition says at least 1 4. So the code must contain at least 1 4, which means that you can have a code that has 4 here, or have a code that has 4 here, or have a code that has 4 there, or have a code that has 4 there. You've used 1 4. How many cases are we having now? 4 cases. We are having a 4 as the leading variable, 4 as the second one, third one, and fourth one. But they said at least 1 4, which means that we start from taking 1 and more, which means that we can also have a code that has 2 4s. Code that has a 4 here and a 4 there. A code that has a 4 here and a 4 there. A code that has a 4 here and a 4 there. A code that has a 4 here and a 4 there. So you again should have 3 4s. They said at least 1 4. It means that the code can have 1 4, 2 4s, 3 4s, and 4 4s. So if you try to resolve this into possibilities, you can see that there would be many possibilities, and hence it becomes a very tedious task for you to can have at least 1 4. So it is better now to use the rule that would say, let us have an arrangement that contains no restrictions, the total arrangement. Then we take away the arrangement that contains no 4. If you take away all the codes that do not contain a 4 from the total codes, you will know that the remaining codes are the codes that contain at least 1 4. So we say we've successfully arranged the rest of the items, because we would be looking at the total codes that can be formed, the overall number of codes that can be formed. And then we take away or we subtract the number of codes that contain no 4 at all. So we'll know that we would obtain the remaining number, or the remaining answer would be the number that represents the codes that contain at least 1 4. So that is how we're going to arrange the rest. Right, let's look at an example. 2 friends, Sizwe and Katleho, take part in a singing competition. There are 8 chairs and 8 competitors, including Sizwe and Katleho. Calculate the number of seating arrangements if Sizwe and Katleho sit next to each other. Obviously, we've worked with this before, so I'll be very, very quick with it. It's Sizwe and Katleho. They sit next to each other. If they sit next to each other, then there will be how many people remaining? If we place Sizwe and Katleho next to each other, there are 8 competitors, so 6 remain. So 6 competitors remain. Since we want Sizwe and Katleho to sit next to each other, we can make Sizwe and Katleho a single object. So if we have them as a single object that can move within an arrangement, then the total number of objects that we can arrange, the total arrangement will then be 7 factorial, because it's the 6 remaining plus the one group that represents Sizwe and Katleho multiplied by, obviously, we can start with Katleho or with Sizwe, so they can interchange positions. So this would be done in 2 factorial ways. So this would be 7 factorial multiplied by 2 factorial. This would give us 10080. So there would be 10080 ways of us doing that particular arrangement. Right, moving on to the next one. Sizwe and Katleho do not sit next to each other. Do not sit next to each other. Now, this becomes a bit of a tedious problem if you're going to then look at all the possibilities. Remember, we have 8 competitors. So you will be looking at a lot of possibilities. All the possibilities where Sizwe and Katleho are not placed next to each other. It would be a very, very tedious task. So it becomes easy to resolve this by using the method of what? Arranging the rest of the items. Because here we're going to then say, for this second problem, we are going to say, okay, B. We are going to say now, we are going to look at the total overall arrangements, all the arrangements. And then we're going to take away the arrangements where Sizwe and Katleho are seated next to each other. Obviously, the remaining arrangements would be the arrangements where they are not seated next to each other. So that is how we can solve or simplify the solution of this problem so that it does not become a tedious task. So if they do not sit next to each other, what we can do is we can say the total arrangement would then be total number of all possibilities minus number of possibilities where Sizwe and Katleho are sitting next to each other. So that is how we can resolve this problem. So the total number of possibilities would be, we have 8 participants. If there are no restrictions, this would be given by 8 factorial. That would be the total number of arrangements that we can have, minus the arrangements where Sizwe and Katleho are seated next to each other. We've already determined that in the first question. So this would be 7 factorial times 2 factorial. So we would have that we have 8 factorial minus this would give us 30240 ways. So those would be the number of ways in which they can be seated. Right, let us try to squeeze in the last one here, C. Let's try to squeeze in C there. Sizwe is placed on the first chair, that is on the extreme left, and Katleho is not placed next to Sizwe. Let's check now. Sizwe is placed on the first chair, and Katleho is not placed next to Sizwe. So we have that if this is the extreme left, we have Sizwe here on the extreme left, and Katleho is not placed next to Sizwe. So here we should not have not have Katlego. Should not have Katlego there. So we need to work out those number of possibilities where we will not have Katlego in that particular position. So we would have Sizwe on the first position, not Katlego on the second position. So we will be interested in the options of not having Katlego in the second position. And then here we will deal with the remaining participants. How many participants will remain in this case? We would have 6 remaining, because we in the first position it should be Sizwe. In the next position we should not have Katlego, and then in the last position we should be arranging the rest of the participants. So the total arrangement in this case would be given by, there's one option of having Sizwe in the first position. So next to him, if it's not Katlego, then it should be the other 6 participants. Because remember, 7 participants will remain. Because Sizwe is in the first position, 7 will remain since we have 8 in total. Out of the 7 that remain, you want to exclude Katlego. And then in the last part here, we then need to arrange the 6 remaining ones, which we can do in 6 factorial ways. So the total arrangement in this case would be 1 times 6 times 6 factorial. This gives us 4320 ways. It gives us 4320 ways. Right, let's move on. Obviously, because of our limited time, we're not going to do this activity as well. So let's check activity 5. Let's look at this complex one. This is similar to the example that I gave you when I introduced you to arranging the rest of the items, where I said at least 1 4. So in this activity now, they want us to have a code that contains at least 1 7, and it's a 4-digit code. If it's a 4-digit code, it means that if they say at least 1 7, you can have 1 7 being used in the codes. Remember, that 7 can be used in any of the 4 different positions. And then we can have, because they said at least 1, we can have 2 7s used at different positions. We can have 3 7s used at different positions. You can have 4 7s. So in this case, you can see that we have a very tedious problem to work with, because we can have a lot of possibilities. But in order for us to resolve this, we said we're going to use the method of arranging the rest of the items. How are we going to do that? We're going to look at all the codes without any restriction. And then from there, we're going to take away those codes that contain no 7 at all. So if we take away those that contain no 7 at all, it means that those that would remain would be codes that contain at least 1 7. So let us go through this quickly. So the first one, they say the code contains at least 1 7, and digits may be repeated. So we're going to start by having all codes. 1 2 3 4, all codes without restriction, and we have a total of 8 codes, and repetition is accepted. So we would have 8 times 8 times 8 times 8 if we don't have any restriction. So this is 8 exponent 4. So this simplifies to 496 codes if we take all the codes. And then we're going to take away, we want to take away codes with no 7. Codes with no 7. 1 2 3 4. If we don't want to use 7 and we want to repeat the codes, it means we would have 7 numbers to use. because these numbers exclude the number 7. So we have 7 options, because remember we have 8 options originally. So we want to take all the codes that do not have a 7. So the first variable, there are 7 options. In the second one, since we can repeat the numbers, there will be 7 as well. So this would be 7 exponent 4, which is 2401. Therefore, in order for us to have the code with at least 117, in order for us to have this code, we're going to say this would be equals to, the total code would be 4096, total number of codes. We take away the codes that contain no 7. So this would be 4096 minus 2401. This gives us 1695 codes. So this would resolve to 1695 codes. Now let's check possibilities where the digits may not be repeated. We're going to take all codes. If we take all codes, then we're going to get that 1, 2, 3, 4. Since the repetition is not allowed, this would be 8 times 7 times 6 times 5. Because we're not repeating, 7 times 6 times 5, we're going to get that it's 1680 codes. And then we're going to take codes with no 7. If we take codes with no 7, then we're going to have 1, 2, 3, 4. Since we have 8 numbers at our disposal, if we're not going to use any 7 in this case, if we're not going to use any 7, remember we have 8 at our disposal. If we're not going to use any 7, it means that we have 7 options or 7 numbers to use. So we can have 7 here, because we are not repeating, we're going to have 6, 5, as well as 4. So this would simplify to 7 times 6 times 5 times 4. This simplifies to 840. Therefore, if we want to work out the code with at least 1 7, this would be, the total code would be the total number of codes. Take away the code that contains 1 7. That contains no 7 at all. So we would have that this would be 840 remaining codes. So that is how you're going to work with those particular codes. So that is how you arrange the rest. Right. The counting principle can also be applied to probability problems. Because of time constraints, I'm only going to do one example with you where we apply counting principle to probability problems. Everything that we've done thus far would be talking about sample spaces, talking about events, but we are doing so as isolated concepts. But now we want to bring them together to probability, to say we can be able to calculate the probability of an event E occurring. So now I'm going to just look at this particular example. This would be the only example that we're going to do as far as application to probability problems is concerned. That is because of time constraints, obviously. So example 7, if you arrange the letters of the word sociology, repeated letters are treated as identical. That's very important. The repeated letters are treated as identical. What is the probability that, you see, the question now, they are not asking about the arrangement. They are not saying how many possible letter arrangements can you have in this case. They are asking about probability. What is the probability that you're going to have the letter or the word that starts and ends with an O? So we are going to define two things here. We are going to be working with the event and the sample space. So let's start with the number of elements that would be in our sample space. The number of elements that we contain in the sample space would be the arrangement that will not have any restrictions. So if you have the word sociology and you want an arrangement that will not have any restrictions, then you're going to have that this would be number of elements in the sample space. The word sociology can be arranged in, let's check, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 9 letters that we are dealing with here. So this would be 9 factorial divide by, since we have repeated letters, in this case the repeated letters are the O's. How many O's do we have here? 1, 2, 3. It's 1, 2, 3 O's that are repeated there. So we're going to divide that by 3 factorial. So the number of elements in the sample space would be 9 factorial divided by 3 factorial. So this would be given by 60480. So this is without any restriction. Now we want to define the event. The event says to us, start and end with letter O. To start and end with letter O, which means that you have O here, you have O there. Then you have to arrange the remaining. How many letters remain? So here, since we have 9 letters and we've started with O and ended with O, we have 7 letters remain. Since there are 7 letters that remain, so we're going to have that the number of elements in the event would be 7 factorial. Divide by, we're not going to divide by anything in this case because there are no repeated letters. So this would just be 7 factorial. 7 factorial, which simplifies to 50, 40. I hope you understand why I did not divide here, but I divided in the sample space because O's were repeated. But here the event says start and end with O. If you start and end with O, then you no longer have any repeated letters in this case. So in order for you to calculate the probability of an event E occurring, you'll be taking the number of elements in the event, divide by the number of elements in the sample space. This becomes 50, 40 divided by 60480. So if you calculate that, 50, 40 divided by 60480, this gives you 1/12. So your probability of starting and ending with letter O would be 1/12. Right, let's now kill off the last one. The last one says the 3 O's would be together. The 3 O's would be together. Now, if we check here, we also need the sample space. Obviously, the sample space would be where there are no restrictions. We've already determined that 60480. That would be the sample space. But now, the event. What is our event? Our event would be the 3 O's must be together. So the 3 O's must always be together. So if the 3 O's are together, the remaining letters, we have 9. And we've isolated the 3 O's. So we have 6 letters that remain. 6 letters remain. So when we perform the overall arrangement, we should arrange the 6 letters together with these O's that must move together. So which means that we treat the O's as a single object. So which means you'll be arranging the O's as a group, 3 O's as a group, which means that you would have these O's as a group and they would be in an arrangement with the 6 remaining letters. So it means that you will have now 7 objects to arrange. So in the event, you would have that this would be 7 factorial. If you remember in the other problems, we multiplied by, we say multiply by 3 factorial. But in this case, we should not multiply by the 3 factorial since the 3 O's are identical. If there were different O's, then it means you are going to have O1, O2, and O3, which can interchange positions. But in this case, because it's identical letters, so the O's are identical, so we will not be interchanging their positions. So this can only be done in 7 factorial ways. So 7 factorial is 50, 40. So the probability of an event E occurring will then be the number of elements in the event, that is 50, 40 divide by the number of elements in the sample space. That is 60480. This simplifies to 1 over 12. So that is how you're going to be working out now this probability, right? If you check here, I had other problems for you to do, but it's not a train smash. Most of the things we've done them, but we've done them as isolated concepts. What you were supposed to then do was to bring in these concepts together. Know that this represents the sample space, know that this represents the event, then probability is given by the number of elements in the event divided by the number of elements in the sample space, right? That would bring us to the end of our counting procedure problem. Remember, you guys, you are now preparing for exams. Remember those targets that you set for each chapter. Remember, if you set target for a specific topic, you should go to previous papers, try to write those papers and mark for yourself to check whether you are reaching those targets. But you do that chapter by chapter. You don't write the whole question paper. You're only going to write algebra, a mark for yourself, compare with your target. If your target for algebra is 20 and you are obtaining marks that are greater than 20, then you can do away with algebra and say, with algebra I'm okay because I'm meeting my target. Let me go to the next topic. In the next topic, you do the same thing. If you are not reaching the target, then you write another paper, you practice more on that topic until you reach your target. Then you move on to all the chapters until you've completed everything. I hope that this lesson was very helpful to you as far as counting procedures are concerned. Remember, I said to you, this was part 2 of the lesson. And if you did not watch part 1 of the lesson, you can go to Pocket School, www.pocketschool.co.za, to check the first lesson so that you can combine the 2 lessons. Right. Thank you very much for watching. Remember to take care of yourselves, study and practice mathematics. Thank you and bye-bye.